Hello, everyone. So we're going to move into the last section of your Unit 3. So in this section, as I mentioned earlier too, we're going to combine chapter 23 and 24 together. That means you are getting one homework and one worksheet for this section. So now chapter 24 is about electromagnetic waves and energy and polarization and those kind of things we're going to discuss. It's a very short chapter, that's why I combine that into here, right? But chapter 23 is very important concept that we're going to discuss in here is electromagnetic induction. So now the principle that we're going to discuss in here will be Faraday's, Lenz, and Joseph Henry's discoveries. So now, before moving into that, think about what you know already. We discussed about electricity, we discussed about the magnetism. But when we discuss about the magnetism, we combine the electricity to the magnetism, right? You remember that one thing that we discuss is if there is electric current, right? If I have the wire piece that will carry the current upward direction, then you're going to use one of the right-hand rule that we learn. We learn two right-hand rule. This is one of that. So you use your thumb to the direction of the current, and then you're going to grab the wire. When you grab the wire, that will be the direction of the magnetic field lines, right? In addition to that, magnetic field very close to the wire is stronger, but when you go away from the wire, it's getting weaker and weaker because you have denominator, you have the R component to that. So now there is a connection between electricity and magnetism because magnetic field have the connection to the current on the wire. That is one way that we connect these two things together. And in addition to that, we discuss about the magnetic force by using electric current inside the magnetic field and by using charge particle moving inside the magnetic field, right? So first thing is, if you have a magnetic field pointing in this direction, I have a north magnet, south magnet, however I create the magnetic field to the right direction. Now, if I bring the wire that has the current moving upward direction, right? So I have the current moving upward direction, and this is magnetic field. So for that, we use the right-hand rule, thumb to your current direction and fingers to your magnetic field, and palm you're going to open to your third direction, right? That is the magnetic force direction. Now, in this case, if I have a current in this direction, only way that I can keep my fingers will be this way, right? So I have 90 degrees between current and the B, then my palm of the right hand pointing outward from my palm. So that means it is into the board. That means I have magnetic force pointing on this direction, right? Towards you actually, right? So that is inward this direction, magnetic force, right? So that's the connection between actually the current and the magnetic force, right? And in addition to that, we discussed that we don't have a current carrying wire, but we have a particle moving inside the magnetic field. So now you have again magnetic field to the right direction, and now you have a particle. I cannot take the particle. So particle is moving on this plane upward. We'll say I have a charged particle moving upward direction, right? So now again your right hand rule will be exactly the same. You have particle moving upward. I'm doing it for if it is a positive charge, and this is the magnetic field direction. So nothing will change. This is the velocity direction now, and this will be B direction, and palm will be going to open into your magnetic force direction. It will be exactly same. That means magnetic force will be pointing towards you, right? So now, if it is a negative particle, what will happen is negative particle has the negative charge. So now you do not change any of the rules that you learn, but at the end, whichever direction of the force that you are getting, this is the force direction I get for the positive charge. When the charge is negative, I just switch the direction into the exactly opposite direction. That means towards me. So that will be the direction of the force for the negative particle. So we discussed those things already, right? So after discovery of this, because electricity can create the magnetic field, that's the main idea that we discussed, right? But after those discoveries, scientists start trying to think about, can we do opposite? What is the opposite means? Opposite means, can we create electricity by using magnetic field? So we never discussed any of the things that we discussed so far. We did not discuss that. So that is a new thing. So can a magnetic field create the electricity? So that is called it as the induced electricity, because since there is no source charge, you're going to create by inducing by inducing the voltage, you're going to create the current, right? That is called it as induced EMF. So now after discover the earlier concept that electricity can create the magnetic field, people try to think about, can we do the opposite? And then after 10 years later, Faraday and Henry, both scientists, independently discovered that actually it is possible to create the electricity by using magnetic field. So now the concept that we're going to learn in this chapter actually related to those Faraday's law and Henry's and also Lenz rule related to this induced EMF concept. Okay. So now let me share my presentation. Okay, so now we're going to discuss because Faraday did actually series of experiment to realize actually what is this induced EMF, induced by what, right? So to understand that, I have the first Faraday's experiment. So what he did is actually he has the coil that is connected into a galvanometer. So galvanometer is we'll say ammeter. It is sensitive to the current, right? So now there is no power supply or battery in this case, because we're going to talk about the induced information. Induced does not have the external power at all, right? So now what he did is, he tried to bring a magnet. You see that the magnet, I have it in here. He tried to bring it closer to the wire, and then he bring it back, and then he keep it constant. But he observed a couple of things in here after doing that. One thing he observed is, when he bring the north towards the coil, there were a deflection on the galvanometer. So that I have the diagram in here, better one. So when you bring the north, you see the galvanometer deflection. And then he tried to bring north downward direction, and then he did the galvanometer deflection, but it is in opposite direction. And then he tried to bring the south, and he did see the galvanometer moving to the same direction as bringing north downward direction. And then he bring the south downward, then he see the deflection to the right, similar to the north bringing upward direction. And then he tried to just stop the magnet closer to the coil, then there was no deflection. After observing this, all the things together, what he thought is, okay, to happen this deflection, there should be some kind of relative motion between coil and the magnet. Then there is an induced current is happening on the wire, right? Then he tried to do the different experiment, second experiment. In the second experiment, your left coil is exactly same as the first experiment, but he changed the second coil, second magnet that you have it in the first experiment into a circuit. So he has the power supply and the coil, resistor and the switch. Then he tried to switch on and off this one. Then he observed exactly same thing as he observed by bringing north and south magnets to the coil. So then what he realized is, nothing to do with the relative motion, but there is something change in the first experiment, same thing happening in the second experiment, but no relative motions, right? So then that something change, Faraday discussed that something change is related to magnetic flux that we discussed in earlier section, magnetic flux. So you guys remember what is the magnetic flux is. Magnetic flux is magnetic field times the cross-section times the cosine of theta. That means basically how many magnetic field lines cross through that surface that your interest will be magnetic flux, right? So that means, as we discussed, if you have a coil that has the magnetic field, coil and magnetic field in this way, I have a coil and magnetic field in this way, coil and magnetic field. Now you see that my magnetic field is pointing this way, but my coil cross-sectional area is perpendicular to the 90 degrees. Because of that, we'll say this way, this is easy. So you have magnetic field and coil is this way, and then you see that magnetic field and coil cross-sectional area are parallel to each other. That means you have cosine of 0 that will give you 1. In that case, you have many lines, maximum line cross the magnetic field through the wire. But if I have a wire in this way, then your cross-sectional area is perpendicular to the magnetic field. In that case, you have magnetic flux is 0. That's the idea about this equation, BA times cosine of theta. So that's something change in the experiment. Two experiment that Faraday did earlier is actually change in B, change in A, or change in angle, right? So by bringing the coil, the magnet closer to the your coil, what you are doing is basically you are probably changing your angle, probably changing the cross-sectional area, probably you are changing magnetic field. Especially you are changing the magnetic field when you bring it closer to the coil, you have stronger magnetic field, right? In the second one, what you are doing is by switching your switch on and off, there is no cosine theta or anything change. What will change is actually B in there. So whichever change, magnetic field, cross-sectional area, or angle that you're going to use will affect to this induced EMF that will be related to magnetic flux that we're going to be discussing in here. Okay. So now Faraday actually make into a formula that we can combine induced EMF into magnetic flux. So induced EMF will be related to the magnetic flux. So induced EMF will be actually change of rate of magnetic flux. Change of rate of magnetic flux, we call it as induced EMF. Epsilon is for the induced EMF. That's the Faraday's law, right? So I did not discuss the negative sign yet because negative sign is coming from another law that we call it as Lenz law, right? But without negative sign, this equation does not make any sense. We're going to come to that in a minute. But if you have n number of coils, that means instead single coil, if you have n turns, then you need to actually multiply by this n number of turns to get the induced EMF. Yeah, that will improve your EMF by adding more turns to the coil. Okay, so now let's move into this Lenz rule, because this negative sign on the equation coming from the Lenz. So that's very important. It's very confusing to get the direction correctly if you did not actually really listen to or really follow the rules. Okay, so now induced current has the direction, right? So now this induced current basically induce EMF to oppose the magnetic flux that induced in the current. What that means is, example, you can think in this way. So now I have a coil as similar to the earlier experiment, coil, and you bring the magnet north towards the coil. When you bring the magnet north towards the coil, what you are doing is you are creating a stronger magnetic field. In this case, a stronger magnetic field to the right direction. It will create a stronger magnetic field to the right direction, a stronger magnetic field to the right direction by bringing north towards the coil, right? So now I have a coil on the right side. So now this magnetic field has the magnetic flux, right? So now magnetic flux created on the coil will be basically try to oppose this magnetic field, or try to create, what you change is here magnetic field. you try to create a magnetic flux that will reduce this magnetic field. One more time. So you originally have the magnetic field to the right, it is a stronger one. So now what the coil do is, coil try to oppose this process by creating magnetic flux in opposite way. That means basically creating magnetic field in opposite direction. That means coil try to create the magnetic field. This is original one. This is magnetic field, coil try to create, right? So to create the magnetic field, what we know that coil should carry the current. That current we call it as induced current. That voltage we call it as induced voltage. Now, how do you find the direction of the current? So you have a coil. You have a coil. That it is hard to sing in here, my hairband. So I have the coil, right? So now this coil, you bring the magnet according to my observation in there, left to right, bringing the magnet this way. So it will create the magnetic field lines this direction. But coil try to create the magnetic field opposite direction by creating the current on this. So now your first right-hand rule that we used to find the direction of the magnetic field when there is a current on the wire. This is the rule you need to use. Now I need to create the magnetic field inward direction inside the wire. That is the direction I should have. So now to have that, you see that my thumb should be going on this direction to create the current. So your current will go in this direction. I cannot say clockwise or counterclockwise. It depends on which direction I'm going to rotate. But according to this rule, my thumb will be going in this side. It is clockwise direction, right? Clockwise direction. So that will create the current. That's the direction of the current. That's why you have this direction clockwise current, and this direction is coming downward. Okay. So that's why that negative sign is there, because it's doing opposed to the what is originally happening. So now in the second case, you're going to bring the north backward direction. When you bring the north backward direction, you basically you still have magnetic field to the right direction, but you try to make it decrease, right? Magnetic field originally to the right, but you try to decrease it. Decrease it means basically what the coil should do is, coil should try to stabilize that into original position. So that means coil has to do something opposite to that. That means coil try to actually increase the magnetic field in this direction. Then that decrement will cancel out with the increment on this side. That will keep your original magnetic field into the right direction. Okay, so always think by using this equation, BA cosine of theta. We did not change any of the A or cosine theta in this case. What we are doing is change in B. When you increase B, right, your flux will increase. Now you need to decrease the flux. To decrease the flux, you need to decrease the B. That kind of thing. So you need to think in that way in your side. Okay. So now the second figure, what is happening is it will decrease the magnetic field. Originally you have magnetic field this way, but by bringing the magnet further away, he's basically keep decreasing the magnetic. He'll try to lower it down a little bit. So now this lowering does not like the coil. Coil like to maintain what he had. Because of that, he tried to do the opposite of that. Then he tried to create the magnetic field in this direction, right? So now if you need to create the magnetic field in that direction, definitely in this coil, you know that you need to create the current by keeping hand in this way. That means my current moving in this direction. Okay, so that's why I have current on this direction in here. Okay. Okay, so now you can practice it by doing the south. What the south is do, magnetic field is to the left, right? Magnetic field is to the left in the south pole. So by bringing the magnet, you make it stronger and stronger, but you need to decrease it. Then your coil try to do the opposite magnetic field, then your current will be that direction. Okay, so that's what the negative sign means. So again, magnetic flux, as we discussed, or induce EMF will be able to change by changing 3 variables or all together, right? You can change B, A, theta, or all of them. Okay, so now next part is EMF induced in moving conductor. So we call it as motional EMF. So when conductor move through the loop, that will create a induced EMF. That's the part that we're going to discuss in here. So now in the image, what you can see is you have magnetic field. So that B is inward into the page, right? And then I have a coil. Actually, this is the conductor that you're going to move. This is a motional part that you can keep moving left and right, but it was originally here and move into this place. Okay, so now what is changing in your magnetic flux is actually you are changing cross-sectional area by moving that. Because of that, you are changing your magnetic flux and also magnetic magnetic flux because of the cross-sectional area, right? So now what is happening is because of this motional conductor, it will create the current on your left side. Right side is open. Left side you have a closed loop. This is your closed loop that you are creating. It was here earlier. Now I have a larger cross-sectional area, right? So now what you need to think, okay, so you have a larger cross-sectional area. That means flux is BA. You don't change the cosine or B or anything. What you are changing is you increase this one, right? So because of that, flux will increase. Now I need to actually decrease the flux, but I am not able to change the cross-sectional area in here. I only need to change the B. That means I need to decrease the B to make your flux decrease. That's the opposite way that you have to do. Now you need to think. It doesn't matter the way you understand, think about the opposing things. So this is my way that I understand. So you can try it in your way. So now I have a coil, magnetic field is inside as I have it in here. So now I need to basically decrease the magnetic field. That means coil should try to create the magnetic field outward direction. This is from the coil. This is from the coil. Coil will try to create the magnetic field outward. Now you're going to use your right hand for the your cord, this one, the conductor, to find the direction of the I first, right? So now if you use the you have the current direction, you don't know it is upward or downward. Only thing you know is your magnetic field in this direction is going inward, but this direction should be outward. That means definitely on this current carrying wire should have current upward direction. That's because of that your whole circuit have the counterclockwise current in here. So this has counterclockwise current, that is the induced current direction. Okay, induced current direction. So now, how do we calculate this induced EMF amount? So this induced EMF amount we will be able to calculate by using the formula that we discussed earlier. Then pi B will be equal to B times A. This is cosine theta is in this case just 1. So because of that, I'm going to write B and delta A over delta T. Then delta A over delta T, because cross-sectional area in this coil will be equal to your L times V, right? So now if you take the L is basically this length, right? Cross-sectional area that you change will be delta X over delta V. So now by putting that into there, I will be able to write this as this equation. But finally, you're going to end up with this one because you have delta V over delta X. Actually, this is delta X over. That's my typo. Delta X over delta L times X, not L times V. Okay, because area is the length and the width that you have, right? So if you have X distance move, if L distance L is your height, then X times L will be the area of that loop that you are changing. So now you will be able to calculate the induced EMF by using B, length of the conductor, times the velocity that we're going to move the conductor, right? So that is, we call it as motional EMF. Okay, so let's see why it's not okay. So now we're going to move into the applications. Actually, there are a lot of applications of this Faraday's law and combination of electricity and magnetism. So one thing is the electric generator. So electric generator basically generate or take the energy by doing the work and transfer it to electrical transmission. So that is that's kind of like things that we have it in here. That is called it as the electric generator, right? Electric generator. And then DC generator will be similar to the electric generator, but similar to the AC generator like electric generator, but different is that there is a rotating loop that is made from kind of split ring called as the commutator. So we have this kind of things that we can do the coil rotation back and forth by using this DC generator. Okay, and motors are device that we can tell it as the energy transfer into some kind of work, as we already know. And the motor basically operate in reverse direction. So when the current is going through the coil by a battery, then torque, there should be external torque that we need to create to make it keep rotating. We discussed that earlier too. So generators, DC generators, motors, then hybrid drive system in your automobiles. So there is a the system that we can connect the gasoline engine with the electric motor combined to increase the economy of the vehicle, right? And induction oven is also important, because induction oven basically using Faraday's law that create a kind of current that will heat it up your the cooking, but it will not give the heat to your hand or to other things that will touch, because it will not like it is created by magnetic field, okay, not by the direct electricity. So other applications, definitely ground pulse circuit interrupter, and also pickup coil electric guitar using that concepts, because we have a small piece of magnetism that will create on this string, and this will vibrate into your this pickup coil, and then you can give it to the amplifier that will amplify your signal. And ground fault circuit interrupter also will include the circuit breaker that we can save basically your home circuit by adding that into the your home devices. And one important thing here, I'm going to plan into actually discuss about the transformer, because transformer also a very important application of Faraday's law. So usually, you know that the power plant will create the electricity, or we have the high voltage from the power plant that we are getting to the home. Then we distribute into the low voltage. So now to convert this high voltage to low voltage to high voltage, we use the transformers. So usually power plant will produce the electricity around 12,000 volt, and then we're going to use the transformer. We call it as step up transformer. Step up means basically you increase the voltage. So now you increase it to 240,000 volt, and then you distribute that into the transmission lines. And then when it comes to the home, we don't want that much of voltage. We just need to reduce it to kind of 240, or sometimes some factories we use a little higher. And then you're going to use a step down transformer to lower the voltage down. So now step up and step down transformers usually build up with the iron core and primary and secondary coil. If secondary coil has more turns, you see that more turns in here. If you have more turns in the secondary coil, you basically create in step up transformer. If you have a secondary coil with less coil, that means you are creating a step down transformer, because your voltage ratio will be similar to the number of turns ratio, but your current ratio will be opposite. Okay? So that's what the transformer, that's the physics behind the transformers. And in addition to that, eddy current is another concept that induction, ovens and those things, we use the eddy current. Eddy current basically is the induced current that make a circular kind of current on the magnetic pieces. Simple example is in your demonstration, probably I have add that video into there. If you have the tubes, if you're going to drop the magnet by using 3 tubes, if you drop the magnet in the copper tube, because copper is a conductor that go through the magnet, it will actually slow down the motion of the magnet. So other plastic and those things does not have the magnetism, just go as a free fall. But in copper or the metal, if you drop the magnet, that will slow down the motion of the magnet, because it will create a eddy current on the surface of the metal, right? So in your diagram here, I have a pendulum bob created by the magnetic metal, right? So then I have north and south magnets. Then it will basically have effect of the eddy current, because it will create the circular current on this metal piece. But here you still have the little bit effect, but here there is no effect, because you using non-conducting material in there. Okay, so that current will be very helpful. Like I have another example in your demonstration videos, that coil, if you have a coil with carry the current, and if you keep the metal piece inside that coil without even touching the current coil wire, that middle metal will be heated up. So because of this eddy current. Okay, so induction ovens that we are talking here also actually concept of the eddy current that we have it in applications right now. And in addition to that, back EMF. Back EMF, we know that when we have a motor that has the rotation because of the current, a magnetic torque will create, right? So when the magnetic flux change according to the Faraday's law, it will create the induced EMF or the induced current, right? So now motor is doing the work, but because of the induced part, it will again do the EMF. That is, we call it as back EMF. So something that you are not doing in externally, but something happening because of the existing current, that is called it as the back EMF of the motor. It is a self-generated EMF that will oppose the motor power, basically back EMF. Okay, and so let's stop here. Not really, actually we need to move into the next part also. I will continue this one another 5-10 minutes, okay? And chapter 24 actually discuss about electromagnetic waves and polarization. So I'm going to jump into this one. So we know that change in electric field can produce the magnetic field, and magnetic flux can produce the electric field. So there is a connection between electricity and magnetism. So now this connection was known before Maxwell put these things into the equations, because Faraday mentioned about that. But Maxwell is the person that combined all the concepts together into mathematical unified theory. So that is called it as 4 Maxwell equations. I know that you don't understand these 4 equations, because those are complex equations that we have differential form and integral forms and those things. But we're going to briefly summarize what we learned and how that related to this four Maxwell equation. So first one, we call it as Gauss law of electricity. We discuss about the Gauss law, right? And then Gauss law of the magnetism, we discussed it like monopole not existing, and Faraday's law of induction, we discussed that. Ampere law, we discussed. Those actually we discussed not in this form, but we conceptually discuss those things. So these things you don't want it, right? So only thing you need to know is first one, Gauss law of electricity is the first Maxwell equation. It is explaining that Gauss law will be related to calculating of electric field from the charge object. That is what the Gauss law is, right? And then Gauss law of the magnetism, second rule is there is no monopoles, right? Because that's the Gauss law of magnetism. And third law, as we just discussed, is the Faraday's law of induction. Change in electric field can produce the magnetic field, and Ampere's law, we'll discuss about the magnetic field can be produced by using electric current in your earlier section. So these four are summarized into this complex equation by Maxwell. So those are, we call it as Maxwell equation. But in this chapter, we're going to focus into electromagnetic waves. After this derivation of the Maxwell equation, this whole four combine into one concept that is called it as change in electric field produce the magnetic field, or change in magnetic field will produce the induced EMF, whichever these two happening together. Because of that, this electricity and magnetism are traveling together as electromagnetic waves that can propagate on the our environment, right? So now this propagation of electricity and magnetic wave together, we call it as electromagnetic waves. Electromagnetic waves. So I think it is better to think about the visible spectrum that we can see. So we know that we can see the colors, right, from red to violet, basically, right? So this red to violet colors that we can see is, we call it as visible light that we can see from our eyes, right? But there are many other electromagnetic waves around us. What are those? Radio waves, right? We have microwaves. We have infrared waves, we have ultraviolet, we have X-rays, gamma rays. Because these all waves are traveling with the same velocity, that is the speed of the light. The speed of the light is the electromagnetic waves speed, any of waves traveling with the same speed of the light, right? So that is the value that we know it in here, speed of the light, right? So now my pen is not working. Speed of the light is this value, right? But important thing is here, you see that in my top axis, this is wavelength, this is frequency. How wavelength and frequency related to each other? We already know that in your physics 116, in this case, speed of the light is the velocity. We use the symbol C for that, equal frequency times wavelength. That means when wavelength increase, frequency should be decreased. That's why I have wavelength in this axis is a smaller value, but frequency is very high value, right? So now this high frequency waves that I have in this range, we call it as gamma rays. Where we use the gamma rays for radiotherapy, or to kill the cancer cells, we use the gamma rays. We have different techniques right now, but gamma rays is the first techniques that we found. It is dangerous for the body, but now we have phototherapy and those things that will decrease the amount of rays going through your whole body. But gamma ray can be used for that. And X-rays, we know that we are taking X-rays when you go to the doctor office, you're doing CT scans. Those are basically X-rays within this spectrum of frequencies. And then ultraviolet is very close to the violet that we can see in our eyes. Ultraviolet is the wave little danger than normal violet, because it will create kind of like skin burning and those things because of the ultraviolet rays, right? But they will use for some medical applications that we can get advantage of that other than burning the skin. And then infrared is basically that we cannot see, but it is a heat waves that when we have the remote controller, when you have oven on, you will feel the heat. That is, we call it as infrared heat that we use for the night vision cameras and astronomy observations. Those things are infrared rays. And then radio waves, microwaves, you know that those things we have it using every day in our life. But these are whole spectrum of electromagnetic waves. We only can see the visible range from around 400 nanometers to 700 nanometers wavelength. Okay. Okay, so now I will briefly discuss this one, not go in detail. Electromagnetic waves traveling together, as I mentioned. So electric and magnetic waves are always traveling perpendicular to each other. As example, if this one is my magnetic wave, this will be my electric wave, right? Then these two together propagate into the direction of this with the speed of light, c. Okay. And electromagnetic waves are sinusoidal waves, as you can see it on the drawing, right? So now they have a constant k, and they have omega angular frequency and those things, as you discuss in your physics 116. But important thing in here, I'm sorry. So important thing in here is the speed of the light is equal to wavelength times frequency. You discuss velocity equal wavelength times frequency, but here is the speed of the light. Actually, you can check by doing a calculation, because you can have c wavelength and the lambda. If you plug those things into here, because c is actually, you will be able to calculate by using electric field over magnetic field. So now electric field and magnetic field are related with the mu naught and epsilon naught. Because of that, if you take the root of this, will be equal to c. So now after you plug this permeability and permittivity on the air, you will get the speed of the light that we know, 3 times 10 to the power 8 meters per second. Okay. So electromagnetic waves will be belong to transverse wave. In your 116 class, we discussed about 2 waves. One is transverse wave and the other one is the longitudinal wave. So transverse wave example is the light wave, as we discussed, and longitudinal wave is the sound wave. Longitudinal wave is traveling by vibrating air particle back and forth, and transverse waves traveling as a up and down motion perpendicular to the direction of the wave. Okay, so electromagnetic wave is a transverse wave. Okay, so electromagnetic waves should have energy. So because of electric field and because of magnetic field. So I will not going to derive any of those equations. From the electric wave, you will have energy density can be calculated by using this equation. Epsilon naught is permittivity, E is electric field. And from the magnetic field, you will be able to calculate by using B magnetic field, and mu naught is permeability. So now by adding the informations that we discussed earlier, you will be able to write this whole energy only by using electric field or by using magnetic field only. Right, that is the energy of the electromagnetic waves. And in addition to that, when you come to the advanced level classes, we are talking about the relation of those things into the intensity. That is, we call it as a Poynting vector. That's the combination of E and B, and that will directly related into intensity of the light. That part I'm going to skip for your class. Okay. And so last part of the section is polarization. So polarization is important concept that everybody have seen, the polarized glasses, right? So usually when the electromagnetic waves come to our eyes, those waves has no polarization. They are unpolarized. The waves that we are getting is unpolarized. That means we can absorb some of the light by using polarization sheet, that we call it as the light will be polarized. But what is the polarization sheet means? Polarization sheet means basically you have a kind of sheet that has molecule embedded to the kind of parallel lines. These are small holes that embedded the molecules. So now when light hit this sheet, what happen is light parallel to that lines will pass through the sheet. All the perpendicular light will be absorbed, right? Then the light you will getting out from this sheet will be just a parallel light with respect to your axis of the polarizer. So now usually unpolarized light, we use the symbol. Sorry, so I'm going to draw it in one more time. We use the symbol unpolarized. This is the symbol for the unpolarized. That means basically I have light in all directions, right? So now if you need to draw a polarized light, we're going to use the symbol with polarized. That means you can draw it this way. This is called it as just a symbol, okay? Polarized light. Polarized and unpolarized light. So now what is actually happening? As a simple example, I have it in here. So you have unpolarized light. You send it to the polarizer. Then you will only pass the vertical light. All the perpendicular light will absorbed by the polarizer. So now the one you are getting, we call it as polarized. That will be your electric wave polarized into one direction, right? So now the intensity of these two will be related to each other. That means unpolarized has the intensity I naught. Your polarized light has the intensity I. You can calculate your intensity of polarized light as half of your original unpolarized light. That is called it as the intensity of your polarized light, right? But this is 1/2 rule. But you can actually send the light through the polarized light through the polarization sheet. So that's the next example. So then if you need to send the light in that way, if you need to send the light on that way, then you need to consider what angle is you going to send the light, right? So now we'll say I have a polarizer that has, I have a polarized light this way. This is you're going to send the polarized light with the I, with some I naught intensity, right? So now you have the sheet. I have the light. I'm going to keep the sheet there, but I cannot draw it in there. I'm going to draw it in full view, right? So this is my polarized light. This is how I'm going to keep my polarization sheet. So I'm going to keep the polarization sheet, but not exactly parallel to the sheet. I'm going to keep it some tilted axis like this, right? So now what you have to do is you need to take the angle between your polarized light that you're going to send and axis of your polarization sheet. That is what I label it as theta in here, right? After that, you're going to get the light, as we know, you're going to get the light as this, only passing through the parallel lights to the polarization axis. Then you're going to get this I in here as I naught times cosine of squared and theta, we call it as cosine rule. So cosine rule will work when you have polarization sheet in front of the polarized light. Okay, then you can pass some of that by using cosine angle. Other things that you always, the student missing is this theta angle. Theta angle is what? It is the angle between your original light and the axis of the polarizer. That means what are the parallel lines you have? This is the axis that I have it in there. Okay. Then you will be able to calculate the intensity of the passing light through the polarization sheet. So I think this is the end of the section, and we're going to do some problems in your recitation session.